Section 7.8 is the last section of this chapter. It's on page 567. It talks about improper integrals. And let me elaborate how this idea works. Suppose I'm looking at you know what? Forget the numbering. F of x equal 1 over x squared. And I am interested in the integral from 1 to t of 1 over x squared dx. So I'm interested in the integral from 1 all the way to some t. Basically, I'm trying to figure out what this area equals. Now, if t equal 1, I'm looking at the integral from 1 to 1 of 1 over x dx. Well, that would be 0. If t equals 2, then I'm looking at the integral from 1 to 2 of 1 over x squared dx. Well, that would be negative 1 over x evaluated from 1 to 2. That would be negative 1/2 minus a negative 1 over 1. That would be a 1/2. And that means this right here, I'm running up to, and I'm using those colors that are a bit hard to see. In this case, I just ran from 1 to 2, so I'm talking about this area. If I am to integrate, if I am to look at t equaling, let's say, 10, then I'm looking at the integral from 1 to 10 of 1 over x squared dx. And that would be negative 1 over x evaluated from 1 to 10. By the way, I forgot to mention, that's x to the negative 2 dx. You add 1 to the power, divide by that. In case you're wondering, how am I getting 1 over x? And that is negative 1 over 10 minus a negative 1 over 1. That turns out to be 9 over 10. So, and this would be, if I was to run all the way to 10, from 1, let's say 10 is right there, that will be this area. What if I wanted to find the integral from 1 to infinity of 1 over x squared dx? What that means, I'm going to look at the graph of 1 over x. And I'm going to really run from 1. I'm enlarging this. And on the right-hand side, I don't want to limit it. I want to run all the way to infinity. Remember, this is the function y equal 1 over x squared, right? And in case you're wondering, there is another piece right there, but we're not worried about that because we're starting from 1. Now, this is an improper integral. Integrals normally, in the fundamental theorem of calculus, it's stated, given an interval, a finite interval between a and b, so the endpoints must be real numbers, and the function that you're integrating must be continuous. That's the only restriction on the fundamental theorem of calculus. So here we have a problem. We don't know what to do with this. Well, somebody said, okay, you know what? Not to worry. Why don't you call that a, integrate from 1 to a, 1 over x squared dx, and see what happens. What do you get? Well, that's going to be negative 1 over x evaluated from 1 to a. That is negative 1 over a minus a negative 1 over 1. So altogether, altogether, this is simply negative 1 over a plus 1. And if I take the limit as a approaches infinity, well, hey, that's kind of resembling the same idea. If I take the limit as a approaches infinity, the limit as a approaches infinity, the limit as a approaches infinity, and what would that be? From chapter 6.8, we did infinite limits. Wouldn't that be 0? That will be 0 plus 1, which is 1. Which means this infinite area is equal to 1. How could an infinite area equal to 1? Just like an infinite sum could equal a finite number. If you recall back from sequences, specifically geometric sequence, right? When we took the infinite series of those, so an infinite geometric series, if the absolute value of r is less than 1, that infinite sum will equal the first term divided by 1 minus r from back in the days. We are going to come back to that in chapter 11. Alright, so let's get a few things out of the way. I want to look at a problem in the book. I want to look at problem number 2 first and get a few things set in my mind to clarify how this is going to work. So first, let's make sure we are clear on what is wrong with these problems. Which of the following are improper? So we dealt with indeterminate forms. Now we're talking about improper integrals. This is on page 574. So, fundamental theorem of calculus, you could review that back, I think chapter 5 is it? There are 2 parts, 1 and 2. Well, the condition on it was that the function would be continuous on the interval, and let me demonstrate really quick the problem with each of those. So, and elaborate on how this is going to apply to us, and so on and so forth. So, they say, which of the integrals are improper and why? Well, somebody might look at this and integrate. When somebody, oh, hey, wait, that's a natural log of, wait, time out. 2 conditions on integration. The fundamental theorem of calculus says, given x to be between a and b, where a and b are real numbers, that's true in this case. The other condition was, this function must be continuous on that interval. Well, what's tan of? So tangent of 0 is 0, tan of pi, well, guess what? This is proper. Meaning this I can integrate. Right? So in this section, you're not just going to jump in and say, okay, look, it's an integral, let me integrate it. And you could tell, if you recall the graph of a tangent, the problem with tangent happens at pi over 2 and negative pi over 2. We didn't reach that, so this is proper. We are fine here. You can integrate like you normally do, but you're not going to jump in this section and just integrate. Instead, you're going to try and figure out what is wrong. Well, look at part B. Oh, come on. What do you think is wrong with this problem? Well, again, you're not going to jump into this and say, oh, well, I know what that is. That's the natural log of absolute value of secant. You're going to first investigate. You're going to say, all right, wait a minute. Let me see. Those are finite. Very good. Tan. Well, I know that tangent is undefined at pi over 2. And this is running to pi. So this is improper. I can't integrate this by the traditional method. And why is that? Because tangent of x is undefined at x equal pi over 2, which is in the interval from 0 to pi. C. Again, I know you see one of those, you think of section 7.4 and you're very excited that, oh, hey, I know about this. I know about partial fraction decomposition. Well, I could do this and work it out. Well, again, these are real numbers, so it's okay. This graph right here, this function, I should say, not graph, this function is not defined at 2, and it's not defined at -1. Do you see that problem? You're integrating from -1. You have a vertical asymptote there. That's an infinite. If I was to look at a quick sketch of this, x equal -1, x equal 2, and at 0 I am at -1/2. So this graph looks like this. And you're trying to figure out the integral from -1 to 1. Here we have a problem. So this is not defined at x equal 2. We have a problem. And as for the last problem, hey, this is always continuous. That's not a problem. But do you see what the problem is? You're integrating from 0 to infinity. You're integrating, now whatever the graph looked like, e to the negative, so at 0 you are at 1. Right? You're integrating all the way to infinity. So that's not a finite number. Right? So, something to look for in this section, not to worry, because on the exam, I will be very specific. I'll give you problems out of the first portion of integration, and when I get to this problem, this will be a problem by itself, and I will say the following directions. Determine whether each integral is convergent or divergent. Well, before I get to that problem, I really need to get a definition in. The time is always a problem in these lectures. So let me jump to this really quick. And here we go. The way it works, we already worked it out, sort of. It says if you're looking at an integral, the function is continuous on that interval, except that interval is infinite. What you do, if you're taking the integral from a to infinity, you throw in a variable in there, and you take the limit as that variable approaches infinity. What that does, that takes you back to section 6.8. In 6.8, when we did L'Hopital, we played with those. Limits. And if you're looking at an integral from -infinity to a number, then we replace that -infinity by a variable and take the limit as t approaches -infinity. In part C, I'm going to leave until I do a few examples. So let me work out a problem really quick. And if I look at problem number 6, well, I know this is 1 plus x to the -1/4. So, if I am to ignore those, even though that's infinity, if I'm just to integrate and say, you know what, this is going to be this is going to be 1 plus x to the, if you add 1 to the power, divide by that, right? And take the limit as t approaches infinity, evaluate that from 0 to t. That would be the limit as t approaches infinity of 4/3 times 1 plus t to the 3/4 minus 1, and that limit will approach infinity. And just like we did back in L'Hopital's, whenever this limit is an infinite or negative infinity, we say this type.